Hello, today I'll be presenting my research titled A Comparative Study of Fog and Cloud Computing for IoT in Smart Cities. This work explores the challenges of cloud computing and IoT systems and highlights how fog computing can address these issues supported by both literature review and simulation analysis. The Internet of Things, or IoT, is revolutionizing smart cities with interconnected devices, optimizing infrastructure and services. Traditionally, cloud computing processes and stores IoT data, but it struggles with latency and bandwidth efficiency, especially for real-time tasks. My research focuses on how fog computing addresses these limitations by processing data closer to IoT devices. Cloud computing centralizes data processing in remote data centers, which is ideal for large-scale analytics but introduces high latency and bandwidth issues. Fog computing decentralizes these processes by using fog nodes near IoT devices, enabling faster data processing, reduced latency due to less propagation delay and transmission delay, and efficient bandwidth utilization. The literature identifies cloud computing as a central architecture for IoT and smart cities, well suited for large-scale data storage and processing. However, its reliance on distant data center introduces high latency and bandwidth inefficiencies, making it less effective for real-time applications. Cloud computing operates on a centralized model, where raw IoT data such as video streams or traffic metrics is transmitted to remote data centers over wide area networks. This results in significant latency, which is uh, unsuitable for time-sensitive systems like dynamic traffic control. Furthermore, the centralized architecture creates bandwidth bottlenecks as the volume of IT devices scales exponentially. Cloud computing decentralizes processing by introducing edge layer fog nodes, enabling local data aggregation and analysis. This architecture drastically reduces latency, bandwidth usage, and energy cost. For example, in traffic management, fog nodes at intersection process traffic flow data locally to adjust signals in real time without transmitting raw data to the cloud. Fog computing faces technical constraints though, including limited scalability due to resource-constrained nodes, physical and cyber vulnerabilities in decentralized deployment, and challenges in ensuring smooth fog cloud task migration. Fog computing complements cloud systems by enabling real-time IoT applications in smart cities, but its full potential requires addressing scalability, security, and interoperability challenges. I'll evaluate cloud-only and fog and cloud hybrid setups based on a simulation of a smart car park system, where it sends image data of the car park to the cloud server for analysis to see if spaces are available or not. The setup overview is something like this, where in cloud only, raw data from cameras sent to the cloud via routers. While fog and cloud hybrid setup, fog nodes pre-processes the data, reducing bandwidth and cloud workload, and then send it to the proxy server, which then sends it to the cloud server. I configured three types of devices. For only cloud-based, there are two, cloud and router, while in the fog cloud hybrid system, there is cloud proxy and fog. Um, Cloud has the highest computational power just to reflect in real life situations, while router, proxy, and fog have moderate uh, power and resources to again reflect real life system. And this all setup is simulated using iFogSim. The simulation results reveal critical differences in performance. In the cloud-only setup, latency increased with the number of cameras due to centralized processing and wide area network delays. In contrast, the fog and cloud setup achieved consistently low latency by offloading tasks to the fog nodes. Additionally, the cloud-only architecture requires significantly more bandwidth as raw data was sent from cameras to the cloud. By contrast, fog nodes in the hybrid setup reduces bandwidth usage by pre-processing data locally, sending only relevant summaries to the proxy and cloud. Analyzing the delays in bandwidth usage provides insights into architectural trade-off. The cloud-only system suffers from high latency, as raw data from cameras travel over wide area networks to a centralized cloud server, where computational bottlenecks occurred. In contrast, the fog and cloud hybrid system uh, demonstrated significant bandwidth savings and low latency, as fog nodes offloaded processing tasks from the cloud. However, managing distributed fog nodes introduces complexity, requiring efficient orchestration and resource allocation strategies, which were not um, demonstrated in the simulation. This study demonstrated that fog computing significantly outperforms cloud-only system for real-time IoT applications in smart cities. In the simulation, latency in the fog and cloud setup remained stable at 215.7 milliseconds compared to 472.7 milliseconds in cloud-only architecture, while bandwidth usage was reduced by 86%. These findings validate fog computing role in reducing delays and optimizing network efficiency for applications like smart parking, also supporting the ones in the literature. Future research will address fog node placement strategies, interoperability with cloud systems, and security enhancement to further advance fog computing in smart cities. Thank you.